All right, so now let's try this one. This one we are not able to use limit of Riemann sums, or at least we're not able to easily use limit of Riemann sums because we don't have a nice little power rule for this one. So let's just use antiderivatives. Now, whose derivative is sine x? Well, we know cosine x's derivative is negative sine x, but there's no negative there. So this must be negative cosine x. Now, when you have a negative in front, the most common error, and we're evaluating that, of course, from 0 to pi, would be to not distribute the negative. Right? So when you have a negative in front of the function, use parentheses so that you remember to distribute the negative. All right, so this would be, so we're going to put parentheses now. So we're going to have negative cosine pi minus cosine 0. So we'll calculate this out first, and then we will distribute the negative. I just wanted cosine 0. Let's see if it'll erase for me. It's probably not happy because I have a pen in my hand. Ever so slowly. There we go. Oops, now I dropped the pen. All right, so that would be negative. Cosine pi is negative 1, minus cosine 0 is also, that would be 1, so that would be minus 1. So that would be negative, the opposite of negative 2, or 2. All right, let's try the next one. All right, so now whose derivative is 1 over x? Of course, that's natural log. So we have natural log of x, and we can put the absolute value bars in there if you want. It's not going to be really all that crucial because we're substituting. If this were the indefinite, we would definitely want those. But you never be wrong with putting those in, even though we're plugging in numbers that are definitely not negative. All right, so now we'll evaluate. So we have natural log of 5. Now I'm going to drop those absolute value bars, minus natural log of 2. We could simplify this using the quotient rule for logs. The difference of logs is the quotient of a single log. So natural log of 5/2. There we go. Let's try the next one. This one is the same thing as the previous one times 2. If you like, you can factor out the 2. And you can factor it right out of the absolute integral sign if you like. So this would be the exact same thing as 2 times the integral of 1 over x dx, evaluated from 2 to 5. So that would be 2 times the derivative of the, the integral of 1 over x, or the antiderivative, would be natural log of x. And then we're going to evaluate that from 2 to 5. And so we'll have 2, and I'm going to use parentheses, right, because it goes in front there. Right? So use parentheses anytime you have a coefficient. And that too is a coefficient. Right? That goes in front of the natural log because it's 1 over x. Right? That's the that's whose so that's whose derivative natural log of x is 1 over x. Right? So we have 2 times natural log of x, and I'm going to plug in, so that's be 2 times natural log of 5 minus natural log of 2, which we know from the previous page that we could simplify as natural log of 5 over 2. And we could use power rule and move that 2 up as an exponent, so that would be natural log of 5 halves squared, and we can even square it. What the heck? Natural log of 25 fourths, and we are done. Whoops, what happened to my 4? How about now? Well, it's making nice boxes, but what about my 4? We're going to get a 4 there. Let's try it again. Yay, there's a 4. All right, let's try the next one. All right, and the easiest one of all, whose derivative is e to the x? Why, it's e to the x, and we're evaluating that from -1 to 1. So that would be e to the first power minus e to the -1 power. And if you like, we can simplify that a little bit and make that, we don't really need the 1. So e minus 1 over e, and that's the exact answer. And we're done with this podcast. Thanks for watching. Some more integration, definite integrals. And in the next lesson, we're going to look at the fundamental theorem of calculus. Bye for now.